Hello everyone and welcome in this module. We are recording this module under the initiative of your own teacher community, and we provide the product guidance and the doubt clearing section on each and every subject related to UG or PG. So if you have any help, like you want any kind of help from us, then you can reach out to us through this website. And in this module, we will be discussing about a very basic subject, which is electrical networks, which is very elementary and like preliminary subject for the both electrical engineering and for the electronics engineering. It is taught on the both in electrical and electronics engineering in like the as a preliminary course. If you look like for most of the electrical and electronics courses, it is like a prerequisite for the most of the courses. If you talk about the electrical machines or power electronics or even analog in the electronics session, so it will be the prerequisite subject. So it is very important for us to know everything about the electrical networks. So as you know, like it will be the prerequisite for most of the subjects. So we will be looking like these electrical network is very much important for both electrical engineering and for the electronics engineering. So it is taught on like in the first semester of the engineering on the undergraduate level. So it is very important subject. So if we look into the complete curriculum, then electrical network can be divided mainly into the 5 parts. So we have divided the complete course structure into the 5 parts, in which first we will be like if we look like the first what will be there in the electrical network, then it is the introduction to the electrical circuits. So in the first part we can see like it will be very introduction kind of thing. So in this there will be some kind of circuits and what will be there, like what are the mainly elements and the components which will be discussed in the electrical network. So all those things will be covered under this introduction to electrical circuits. And apart from this, we will be having we have and another thing which is network analysis. So in this we will be discussing about the various kind of analysis which will be done in the electrical networks. So this is the second part. In our third discussion, we will be discussing about the single phase AC circuits, in which we will be doing some AC analysis on the various electrical networks. And along apart from this, in the fourth part, we have network theorems, in which there are lots of kind of the network theorem by which we can deal the various kind of the problems and the electric like type of the circuit in the electrical network domain. So all those theorems, there are like a lots of the theorem, like 14 or 15 electrical networks theorem which is discussed under the network theorem section. And after that we have another like special design chapter which is known as the magnetic circuit. In that magnetic circuit part we will be discussing about the various kind of magnetic circuit. So we have some kind of magnetic circuit we can't analyze, so we will be drawing it electrical counterpart and doing some kind of analysis in the magnetic circuit. So that kind of study is also covered under the electrical networks. So this is the majorly 5 parts in like which are covered under the electrical network section. And sometimes there is uh, another thing which is graph theory. So that is also covered under the electrical network, but that can be covered under the network analysis also. So that graph theory can be also taken as a like a key course element under the electrical networks. So let us take one by one and we will see like what are the things in comes under these 5 courses. So let us first discuss about the introduction to the electrical circuits. So in the introduction to the electrical circuit, there are like the concept of the network and the circuits. Like what are the like actual will be there in any network or any circuits. Suppose that there are any kind of network or circuits is given, then you have to like have a view like what are there in the generally what are there. So if you have any kind of network or circuit in the electrical network, then maybe there will be a kind like some kind of components over there, like some voltage source, some current source, some resistors, uh, capacitor and inductor. So these are the like for if you talk about the major electrical network, then these are the 5 main component which we will be generally looking into the electrical network. So if you talk about the general component, then it will be the voltage source, current source, resistor, inductor, and the capacitor. So these are the five general components which you will be finding in the electrical network. Apart from this, there are lots of elements which are there, like diodes, Zener diode, or maybe transistors. So these elements also are there in the electrical network. So there are lots of kind of components are there, but these five, like which I have told you, voltage source, current source, register, inductor, and the capacitor are the major component which you will be generally encountered in the electrical networks. So after that, we will be discussing about the type of the elements, which are the like what are the types of elements, like on the basis of their characteristic. The elements can be divided into various types, like linear elements, non-linear elements, passive elements, active elements. So these kind of study is done under the types of elements. So we will be like dividing all those elements in on the basis of their characteristic into the various type of element. So after this, if you want to like have any idea about the sources, then we will be discussing about the type of the sources, like what are the various type of the sources you will be generally encountered in the electrical circuits. So like the voltage source, current source, and voltage dependent voltage source, current dependent current source, or voltage dependent current source. So these type of dependent source, independent source are discussed under the type of sources. And apart from this type of the sources, we have the source transformation also also covered in this chapter. So in the source transformation, we can transform one source into another kind of source. Like suppose if you have some kind of voltage source and have a series resistance, then you can do a transformation between the voltage source and the current source. You can transform it like voltage source into the current source by the source transformation, and vice versa can be also done. Like if you have current source, then you can transform it into the voltage source at the same time. So these kind of source transformation is also possible in the electrical circuits analysis. And after that, this RLC parameter. So this we have already discussed, like this will be generally encountered elements, so it will be there in the electrical circuit. So we will we have to have some kind of like basic knowledge about these RLC, what are their voltage and current relationships. So these relationship we have to have some kind of idea, like how the current in those elements varies. If we applied some kind of voltage, then how what are the characteristic of those elements. So these things are also covered under this. And after that, we have some kind of like a very key rule for that electrical network. So all the electrical network, if you look into, then it is mainly based on that Kirchhoff's law. So we have two law, which is known as like very famous law for the electrical circuit. One is the Kirchhoff voltage law, and one is the Kirchhoff's current law. So these two law are the like backbone of the like whole electrical circuit analysis. So these two laws also discussed under this chapter. So Kirchhoff's law are like very much important for the electrical circuit analysis. So these things are also will be there in the introduction, like very basic introduction of the electrical circuits. So let us now move to the second part of our study, which will be there like in the electrical circuit analysis. So in this, we will be mainly dealing with the network analysis. So what will be there? So first we will be having the network reduction technique. Suppose you have some kind of network is given some kind of resistance, some kind of a capacitor, a lots of complex circuit where there will be lots of capacitor and lots of register, and maybe sometimes there will be lots of inductor. Then you have to some idea like how you can represent the complete circuit by like a few elements. Suppose if you have five registers, then you can there is a like possible way that you can represent all those five registers with the equivalent single registers. At the same case for the capacitor and the inductor also. So these techniques are like how you will be converting the complete complex circuit into the few elements. Like suppose if you have five resistor, three capacitor, and one inductor, then you can like completely represent by one resistor, one capacitor, and one inductor. So these techniques by which we will be doing that is known as the reduction techniques, by which you can reduce all those networks. So you have the resistive network or inductive networks and the capacitive network, three different types kind of networks will be there, and you have to reduce all those networks. Suppose you have 5 or 10 complex connected registers, then you have to know about like how you can reduce this in a single equivalent resistance. So that technique is known as the network reduction technique. So there will be some kind of topology, parallel and series topology, by which you can reduce all those circuits. And these are like serial, parallel series. These things are there to like connect any kind of circuit. So if you have like two elements, like suppose you have a register and two registers, so you can connect it in the series or parallel. So there will be like, if you have any complex type of configuration, then all the elements may be connected in the series or parallel. So you have to identify those part, and you have to try to reduce all those techniques, because we have some kind of set of rules by which we can reduce some kind of parallel and series connected elements. So after this, there is another important thing, which is like very important topic for the network analysis, that is star to delta and delta to star transformation. So suppose you have a star network. Star network means like uh, the components are connected in the star configuration or Y configuration. Sometimes star is also known as the Y configuration. So suppose you have a star configuration, and you want to do it into the delta. Delta means the component will be connected into the triangular configuration. So the Y or star configuration and delta configuration are equivalent to each other. Both can be converted into each other by taking some kind of rule. So that is also discussed under this, like how we can convert the star to delta or delta to star. And apart from this, we have the mesh, super mesh, and DC excitation. So mesh, super mesh, these are simply a KVL, which we have already discussed. Those are like the Kirchhoff voltage law. So in the mesh, super mesh analysis, we will be applying the Kirchhoff voltage law, and we will be calculating some kind of unknown quantity. So if you have any kind of the network electrical circuit, then you can apply the mesh analysis or super mesh analysis. So these are like very powerful tools which are based on the KVL, which we can do analysis on the electrical networks. Same as the nodal analysis, super node analysis for the DC excitation. So node analysis and super node analysis is based on the KCL, like Kirchhoff's voltage law, which we have already discussed. So these can be also done to like analyze any electrical network. So these two techniques, mesh analysis and the nodal analysis, are two most powerful way by which you can analyze the complete any network electrical networks. You need not to do anything else beyond this mesh analysis and the nodal analysis. So if you want to analyze any circuit, then you can apply these two analysis. You can get anything from that circuit. So as I have told, like sometimes we also covered this graph theory also. So if you want to know like about the graph theory, then this is also covered under the network analysis. So network topology means like there is another topology in the network circuit analysis, which is graph topology, in which we can represent all the component with their like equivalent impedance, and all those elements are represented by simple a single line. So those analysis is separate analysis, which is based on the graph theory. So in that we have to know about the graphs, tree, basics of tie set, basic of cut set, elements of the tree and graphs, tree twins. So these terms will be there in the graph theory. So that analysis also covered under the network analysis. So that is also very important analysis. So by that you can do any kind of like calculation and all those things you can do with that. So that is also like very important thing for us. So that is also covered under the network analysis section. So these are the like basic thing which is covered under the network analysis. And these are like if you talk about the various other subjects, suppose electrical machines or power electronics or analog and electronics. So these terms will be always generally encountered you like very frequently. So you have to have some basic idea of these things. So electrical network, if you want to do any kind of course related to electrical engineering or electronics engineering, then you have to know about the electrical network. So these are like very elementary subjects. So This thing has to be like very, you have to very crystal clear concept on the electrical network analysis, otherwise you will be facing lots of problem to do any kind of course related to electrical or electronics engineering. So you have to be very careful in this subject so that you get a very like key idea like how we will be dealing all those electrical circuits. Let us move toward the third part of this network, like network analysis. In the third part, we will be having the single phase AC circuit. So sometimes we deal the three phase AC circuit also in this unit, but suppose we have some kind of single phase AC circuits. So in the single phase AC circuit, we will be must have some idea about the average value, RMS value, and the form. Some kind of these are the, if you look into the first line, then it is average value, RMS value, form factor, peak factor, and the different periodic waveforms. So if you are dealing with the like the AC circuits, then you have to have some kind of information about the what terms will be there in the related to AC. So suppose if you have any kind of AC source, so you have to know about the average value, like if you have suppose A sine omega t, which is the value of the AC source. So you have to idea like some idea like what will be the average value of that waveform. Suppose you have some kind of periodic waveform, then how we can calculate the average value, how we can calculate the RMS value, and this form factor, peak factor, and the you have to some idea about the different periodic waveforms. So these RMS value, average value are very like form factor, and these terms are very important for any kind of periodic waveform. So the calculation of RMS value, average value, and these terms is also covered under the single phase AC circuit. So if you have any kind of periodic waveform, then you can find out the RMS value, average value, and all those value for that periodic waveform. So this calculation is also covered under the single phase AC circuits. And after the single phase AC circuit, there is another notation which is known as the J notation. Sometimes we told it as a I. So as we are dealing with the current quantity like frequently in the electrical network, that's why we have not like mathematics guy kind use like I term for the imaginary number. You have heard about this imaginary number, which is under root minus one, that is denoted by sometimes I, sometimes J. So electrical guy and electronics guy use J notation for that. Sometimes you will be see like mathematics guy use I terms, but we are dealing with the electrical networks, and sometimes we are taking I as a current very frequently. That's why we take J notation for that. So we replace that I with the J. So here J is a like imaginary number which is under root minus one. So that J notation is very important in the single phase AC circuit because we are dealing with the like complex quantity. So that J notation is also, you have to some idea like what are the complex polar form representations. Suppose you have A plus IB kind of thing. So A plus IB, this is the like of a complex number. So this is the Cartesian representation of any complex number, that is A plus IB. So if you look into A plus IB, then A is the real part and B is the imaginary part of this complex number. So in the J notation, you will be having the A plus JB. So the same I, what is the A plus IB represent, the same represent the A plus JB, because we have simply replaced the I with the J. So that J notation is very important in this AC circuit analysis because we will be dealing the complex quantity. So that A plus JB can be represented in the polar form as a magnitude as A square plus B square whole under root, or like the magnitude of the complex quantity is under root A square plus B square, and the phase of this complex quantity, suppose you have A plus JB, then the magnitude will be under root A square plus B square, and the phase will be tan inverse B by A. So that is the polar representation in which we can write a complex quantity into its magnitude and the phase form. So sometimes we will be dealing with the complex quantity in the Cartesian form, or sometimes we will be dealing it with the polar form. So both are the same representation. These are like on the your convenience on which you feel face more convenient, you more convenient, you can follow those notation. If you are in like Cartesian, like if the calculation are easy in the Cartesian form, then you can go with the Cartesian one. And if it looks easy in the like polar form, then it is like on you, you can do the Cartesian calculation or polar calculation. So as you will be dealing with the complex quantity, so these notations are very important for that single phase AC analysis. So like after that notation and all those things, you will be dealing like what are the steady state and the transient state in our response of that RLC circuit. Suppose you have some kind of AC excitation to any electrical network, then it will be not settling at the same time. So there will be some kind of transient response during the starting phase of that excitation, and after that you will be getting the steady state response. So that transient and the steady state response of the RLC circuit is also covered under the single phase AC circuit analysis. So there will be a lots of kind of under damped or over damped or critically damped, this kind of response of those RLC circuit, or it may be like series connected or parallelly connected RLC circuit. So on the basis of that, there will be such kind of response like uh, under damped or over damped or this kind of. So these analysis is also done under this chapter. So after this, you have to have some idea about the reactance, impedance, and the subsistence and the admittance. So these are the terms which are related to the impedance. Suppose you have a parallel like series connected RLC networks. So you have, if you have to find out the if you ask to find out the value of the impedance, so it will be the simply the phasor division of that voltage and the current. So you will be getting some, suppose you have the phasor voltage as a B and current through these elements, like if they are connected in the series is I, then the phasor division of that B and I will give you the impedance. So that is the concept of the impedance. So impedance in the form of like it will be in the form of A plus IB. So the impedance, it is the combination of the reactance and the resistance. So the real part of that impedance will be the resistance of that network, and that imaginary part that will represent the reactance. So the impedance, then substance and admittance, like admittance is the uh, opposite of that reactance. If you take inverse of the reactance, then you will be getting the admittance. So like impedance, if you take like uh, inverse of that impedance, then you will be getting the admittance. So these concepts are also important because we will be dealing some kind of like, sometimes we will deal it into the impedance, or sometimes it is in the terms of the reactance, or sometimes it will be in the terms of admittance. So these concepts are also very much important into the dealing with the single phase or three phase AC circuits. So these things you have to also know. After that, you have to know about the phasor and the like what are the phasor and what are the phase differences. So suppose you have some kind of voltage and the current, and so if you look into the phase of that quantity, suppose you have a sine omega t, then this omega t represent the phase of that quantity which you have. Like suppose you have a sine omega t, then omega t is the phase of this. And like just suppose there is another quantity which is represented by a sine omega t plus phi. So this the first quantity which is having the phase as the omega t, and the second quantity which is having the phase as the omega t plus phi. So you look like there are certain phase difference between those two, because first one having the phase as a omega t, and the second one is having the phase as omega t plus phi. So there is a phi phase difference between these two. So you have some idea like what are the phase and what are the phase difference between these two quantities. So that is also like very much important into the single phase AC circuit. Apart from this, we have the concept of the power factor, real power, reactive power, and the complex power. So related to any circuit, on the basis of the value of the voltage and the current phasor, we have three quantity, like three different kind of the powers, which is known as the complex power, real power, and the reactive power. So complex power will be in the form of the A plus IB, which will be some kind of a real part and the imaginary part, and that complex power is made up of real power and the reactive power. There will be some certain real power and some certain reactive power. So that make the complex power. So if you look into any AC circuit, then there will be certain real power is related with that circuit, and there will be some reactive power is also related with this circuit. So the in the whole, if you look the real and the reactive power, then this complete thing is known as the complex power. So and on the basis of these two real and the reactive power, there will be certain the power factor of the circuit. So that is also very much important for that AC analysis of the circuits. So let us move to the fourth part of what will be there in the fourth part of our analysis in the network theorem. So I have already told like in the fourth part we will be having a lots of kind of the theorems on in which we will be discussing a lots of theorems. So I have enlisted some of those theorem which are discussed under the network theorem chapter. That those are, let us see that Thevenin theorem by which we can represent a complete circuit by a single voltage source and a series connected impedance. So by that Thevenin, if you have some kind of complex circuit, then you can represent it with a single voltage source and a series connected impedance. So that is the Thevenin theorem. Apart from Thevenin theorem, we have a lots of also other theorems also like Norton, by which we can represent a complex circuit into a current source and a parallelly connected impedance. So that is known as the by which there will be some certain kind of set of rules by which we can do that conversion, and that is known as the Norton theorem. Apart from that Norton theorem, we have some maximum power transfer theorem. This is also a very important theorem by which we can calculate the value of the impedance by if you connect across the load of that network, so that the maximum power occurs with that load. So that is the known as the maximum power transfer theorem. Apart from the maximum power transfer theorem, we have superposition theorem, reciprocity theorem, Theilligan theorem, a lots of kind of theorem which I have enlisted. Some of them are also not enlisted here. So there will be a lots of kind of the network theorem which we will be dealing under the network analysis. So let us move further and talk about the last part of that network analysis, that is the magnetic circuit. So suppose you have some kind of core. So you have maybe you have heard about the magnetic cores by which we can produce some kind of flux inside that core. So suppose you have some kind of coil and you have some kind of core and you are producing some plugs into that, then you can't do the analysis with that hardware type of things. You have to do some electrical modeling of those uh, magnetic circuits. So we have some set of rule by which we can convert the complete magnetic circuit into the electrical counterpart, and we can do the analysis. So for that we have some kind of rules by which we can convert all those magnetic circuit into the electrical counterpart. So after conversion, that my converting that magnetic circuit into the electrical power counterpart, we can do a lots of kind of analysis like Faraday's law of electromagnetic induction. This is the the core part of that magnetic circuit analysis. So we have the Faraday's law by which we can analyze the whole magnetic circuit. So we have to look into the Faraday's law of electromagnetic induction, concept of the self and the mutual inductance, that is also covered under the magnetic circuit. Dot conversion, it means the dot conversion means simply the you can note it as a direction of the flux. So that conversion is also covered under the magnetic circuit, coefficient of the coupling and composite and the magnetic circuit analysis of the series and the parallel magnetic circuit. So these are the topics which are covered under the magnetic circuit part. And in this, we will be what we will be doing first we will be converting the complete magnetic circuit into the electrical counterpart, and after that when we will draw the electrical counterpart, then we have the tool by which we can do the analysis on the magnetic circuit. So suppose we have that electrical counterpart of that magnetic circuit, and we want to do the analysis, then we can apply this Faraday law to do the analysis on the magnetic circuit. And after that, applying that Faraday law, we have to have know about the concept of the self and the mutual inductance. So inductance is the major part of that magnetic circuit analysis. You will be frequently facing this inductor in the magnetic circuit, because by the inductor you can produce the flux. So that is the core part of that magnetic circuit. So these analysis, like if you have two inductor, then how you can connect it in the series, and on the basis of the dot conversion, how you can find out the actual self inductance of the circuit. These things are also covered under the electrical network. So this is the whole thing about the complete magnetic circuit analysis. So we will restrict our discussion till here, like what are the things where will be there in the magnetic circuit, like a complete electrical network. So if you have any kind of doubts related to this subject or any other subject, then you can reach out to us. We will be very happy to help you. And if you have any doubt related to this electrical networks or any kind of UG or PG level subject, you can reach out to us to our website. And also, if you have any doubt regarding you want any guidance regarding your project, coursework, and anything, then also you can reach out to us. We will be very happy to help you. We are your own teacher committee, and you can reach out to us for any kind of help. Thank you. Thank you for joining this session.